Hello everyone, welcome to this video. In this video we'll be discussing about deviatoric and hydrostatic conditions of stresses and strain. Further we will be seeing what is the concept of Poisson's ratio, why it is important, why it is being exhibited by many materials, and how different Poisson's ratio is the value of Poisson's ratio is between different materials. Further, we'll be seeing a stress strain diagram and how a stress strain diagram is constructed, and this will lead us to the understanding of one of the very important topics in which the stresses and strains are related, and this is a generalized Hooks law. So we will start by understanding what is the state of deviatoric condition of stress or strain or a hydrostatic condition of stress or strain. So now you know that let's take our very familiar example of a beam, a 3D beam, which is being loaded by a load P. So once a beam is being loaded by a load P, on the application of this load, this beam will deform. This beam will deform in 3 dimensionals. So a deformation is experienced by this beam, and along with the deformation there will be some change in its volume also. It will shrink also on the application of the load. This happens like a rubber band. When it is stretched, it gets thinner. So I'll tell you further that this kind of effect is also is known as Poisson's ratio. So this happens whenever load is applied on a deformable body. A body may be reacting in 2 ways. It will change in its volume and it will change in its shape. So a general tensor, whether it may be a stress tensor or it may be a strain tensor, any 3-dimensional tensor, when it gets deformed, deformed by a load, it may be having 2 types of conditions. It may be changing its volume, it may be changing its shape. So it may be a volume change and it may be a shape change. Apart from these 2, nothing can happen. A deforming body can only change its volume or it can change its shape. So once this happens, we will see that this volume change and shape change is basically called as a hydrostatic condition and a deviatoric condition. So basically a stress, if I'll talk about a stress tensor, then a stress tensor can be decomposed into a hydrostatic stress tensor and a deviatoric stress tensor. Now this is important because once we will be discussing some failure theories, we'll be looking towards it that the failure theories are very closely related to the shape change of the body, because once the load is applied, a body gets deformed and its shape is changed. So a failure theory is very much related to the deviatoric condition of the stress tensor. Similarly happens in the case of strain also. So that's why I wanted to cover this topic separately. So if I talk about a general stress tensor, let's talk about stress. So if I talk about a general stress tensor, sigma ij, then sigma ij can be decomposed into let's bear with me, P delta ij and S ij. Here P delta ij is a hydrostatic stress and Sij is a deviatoric stress. This is a deviatoric stress tensor and P is a P is a hydrostatic stress tensor. Remember that this is P and this is delta Ij. I have told you earlier in the case of principal stresses that the condition of delta Ij when is being applied here, that means a stress tensor is only operating on the principal stresses. This condition of delta Ij is only operating in case of normal stresses or principal stresses. That means this condition is only normal. Normal stresses will exist. So a stress tensor can be decomposed into hydrostatic and deviatoric. So your P is also called as mean stress because only normals are considered here. So they can be a sum of the normal stresses, and this is a mean stress divided by 3. And we also know that in a condition of invariance, our I1 is such like that. Sigma xx yy zz is our I1 divided by 3. So your mean stress is like I1 by 3. This is your mean stress kind of. And you know that. So P becomes sigma xx yy zz by 3. Delta Ij condition is important because delta Ij condition will only extract the normals from the stress tensor. Again, I'll reiterate you, delta Ij will be 1 when I is equal to j. That means for normal stresses. And for I j equal to 0, that means shear when I not equal to, j. This is a condition for delta Ij. So P is a mean stress, and it is represented as xx yy zz by 3, which is also called as I1. I1 is a stress invariant, first stress invariant for a stress tensor. So how to obtain deviatoric one from this? So deviatoric Sij can be extracted by subtracting the mean stress from the stress tensor. Now you look at this. So how will it look like? It will look like sigma xx minus p tau xy tau xz tau xy sigma yy minus p tau yz tau xz tau yz sigma zz minus p. So this is your Sij, which is also called as deviatoric condition of stress. And something very similar happens to the strain also. Just remember this. So this is your deviatoric condition. So as I told you that especially the deviatoric, what does it do? Deviatoric is directly related to the shape change of the body, and whenever a load is applied, a body changes its shape. It may change its volume to some extent, depending upon its stiffness, but it does bring a lot of change in its shape. So that is what we are interested in because this may going to change the failure also of the material. So material may get fail also. So this condition will be very important for us. So since it is bringing out the shape change, so a deviatoric stress tensor is a very important quantity or an entity, and the principal values of this deviatoric stress tensor will be very important for us. So how to obtain the principal values? Sij minus S delta Ij, exactly the same procedure as we have applied for the principal stresses, and S cube minus J1. Earlier we have said I1 for a stress tensor. For deviatoric tensor, we'll call it as J square minus J2 S minus J3 is equal to 0. This is the same characteristic equation, a cubic equation. This will lead me to 3 principal stresses. But I wanted to know what will be the what will be the stress invariance, because as we will see in the failure criteria that stress invariants are very much important for the failure of the material. So a deviatoric, this one J1, J2 and J3, this actually when expanded will lead to equal to 0. The first one is equal to 0. J2 is equal to 1 by 2 Sij Sji. Sij Sji. And J3 is equal to determinant of, this can be further expanded, Sij, a determinant of the Deviatoric stress condition. So these three stress invariants will be very important to you. And what does this gives an information? J1 is 0. That means a hydrostatic stress tensor describes a pure shear state. That means the hydrostatic stress tensor describes a pure shear state. That means all the three components will be 0 here. All the three components will be 0. And J2 is a very, very important term here. J2 is a second invariant. And remember, always remember this, that J2 is very closely related to the shape change of the body. Shape change of the body. And you will find it in many of the equations of the von Mises distortion energy theory, failure theories that we are going to encounter. So this J2 is basically what it is. It is an invariant of the Deviatoric stress tensor. Invariant of the Deviatoric stress tensor, which is directly related to the shape change of the body. And in some of the failure criteria theories, J3 is also used. Otherwise, J3 is also somewhere used in deriving the relationships of the higher stress tensors. So, but I would like to tell you about this concept because this is directly related with it. So now we will discuss a bit on what is the Poisson's ratio. Poisson's ratio. So before understanding the Poisson's ratio, it's important to understand the Poisson's effect. Poisson's effect. And Poisson's effect is very important because what happens in Poisson's effect, it's a kind of some kind of phenomena in which a material tends to expand or contract in the other direction of the loading. For example, let's say I have a simple material in a 2D and I'm elongating it. I'm putting a load along only in one direction. And let's say the length is L1. Along this, the length is L1 and the other length is L2, or the width is L2. Length is L1 and the width is L2. So in this condition, if I am loading this material, every material in some way or the other, when gets loaded, then its reaction will be somewhere like this. It will expand in the loading direction. It will expand. So this is the expansion. This is the expansion delta L1. This is the expansion. Expands in the loading direction, but it gets contract in the non-loading direction or transverse direction. It will contract. This usually means this usually happens for most of the materials. Whenever you load a material along a loading direction, along the loading direction it expands, but it contracts along a non-loading direction or a transverse direction. So Poisson's ratio usually is represented by nu. And why it is called as a ratio? Because it is the ratio of negative of transverse strain. Transverse, always remember, transverse means the strain in the other direction, the non-loading direction, and the axial strain. Axial strain means the strain in the loading direction. So that means your transverse strain will be epsilon 2 and your axial strain will be along the loading direction epsilon 1, or you can say xx or yy also. So your epsilon 1 is delta L1 upon L1, epsilon 2 is delta L2 upon L2. So these are your strain value. So what is the Poisson's ratio? It's the negative of the strain, transverse strain by the axial strain. So this effect of transverse, or this effect of this Poisson's effect, is shown by many materials, and the Poisson's ratio of stable linear elastic isotropic material usually varies between -1 to -1 to 0.5 usually. I'll tell you what this is. So what happens usually, a linear elastic material which behaves linearly, and it is also elastic, and an isotropic material. Isotropic material means a material for isotropic material, the properties will be same in all the three directions along x, y, z. So it will be having same properties in all the direction. Linear elastic isotropic material, this is the most usual common material that we use to that we are using in day-to-day's life. So in that case, the Poisson's ratio remains in between -1 nu smaller greater than 0.5 on this condition. That means Poisson's ratio remains within this condition, 0.5 to -1, in this range only. This condition is why this condition is there. This condition is basically restricted because there are some elastic proportionality constant E, G, and K, and we will discuss about this E, G, and K in this video only. In the further later part of this video, what is E, G, and K. So there is some kind of a relationship between them. To maintain that relationship, that they remain positive in nature, because these are the Young's modulus, and this is the bulk modulus and shear modulus. So they remain positive throughout. So that's why this condition occurs. So we'll talk about this further. So in usual condition, let me give you a small values of this. So most of the steels, aluminum, have the iron also have a Poisson's ratio in between 0.25 to 0.35. 0.25 to 0.35. Usually in this range the Poisson's ratio is. It's very important here to discuss this. For case of a rubber, the Poisson's ratio is approximately equal to 0. For case of a rubber, Poisson's ratio is approximately equal to 0.5 for a case of a rubber. That means it is at the highest value. Because rubber is very, very elastic. And once you increase it in one lateral direction, so usually it also gets very thinner. So overall the ratio becomes 0.5 only. So further, one other important thing is about cork. Cork is in the bottles of cold drink, in the bottles of some other bottles also, in which it needs to be preservative. You have seen that these glass bottles are contained of, on the top of it they are contained of this cork, which is opened by a key, mostly in cold drinks or in tomato sauce bottles you have seen. So in that case, as you see, the cork is not expanding laterally on the application of the gas pressure. So cork Poisson's ratio is very close to 0. And there are some polymers also. Some polymers, foams like in beds, they exhibit negative Poisson's ratio. They exhibit negative nu in most of the cases. So there is a lot of study that may be done further towards it. In any of the standard books you can see this condition in which the Poisson's ratio remains within this limit, -1 to 0.5. It remains within this, and this is because due to the condition that some restrictions are there on E, G and K, and what these are I'll be going to describe you later. So this is what the Poisson's effect is. So Poisson's effect actually gives rise to a Poisson's ratio, and remember that it is negative, it's a negative of transverse strain to axial strain. Now let's discuss about a stress strain diagram. This is very important. This will lead to the generalized Hooks law. So stress strain diagram. So in the stress strain diagram, let me first give you an example. We'll take an example of a rod, okay, and this is a bar or a rod which is being loaded from both these axial location, and this rod is being loaded. So once a stress is applied, the axial stress is applied on this rod, there will be corresponding strain existing on this rod also. So if I measure the stress and strain, and I have already told you how to measure the stress. This stress strain measurement is done on UTM. This is a machine. It's run as Universal Testing Machine. And how we will measure the stress? The stress is measured by a load cell. Load cell measures the amount of stress being pulled by this saw, and the strain is usually measured by the extensometer, which is also but we have only discussed strain gauges, so you can just say that you can put one strain gauge here and one strain gauge on the other side, and you can measure the strain epsilon. So you can measure stress and strain. So if I'll plot a graph of stress and strain, let's say on my x-axis we have strain, y-axis we have stress. If I load this material in the UTM, then how will my let's say I am talking about aluminum, Al, or let's say I'm talking about iron. So I am loading the material now. Now as I load the material, as the stress will increase, there is some kind of deformation also occurring inside the material. So the graph usually varies like this. As the load is increasing, there is an increase in the deformation also. So I can make some kind of a relationship. This is valid for almost all material, whether it's iron, aluminum, copper, magnesium, steel, and so on. So all these types of metals usually show an elastic behavior. So this kind of slope, this slopes remembers me of a condition y equals to mx plus c. If my condition my constant is 0, so this y on the y-axis becomes sigma, this m becomes something that I don't know, and x is my strain. Also, in other ways, my stress and strain are proportional. That means stress is proportional to strain, and the proportionality constant may be m. So at this point, if at any point in this I would like to know the slope of this curve, the slope of the curve will be sigma upon E. Sigma upon E will be the slope of the curve, any point on this curve, and the slope of the curve is usually represented as E. There is the same E here that comes for the Poisson's ratio. I'll discuss more on this. sorry, this is epsilon, this is sigma upon epsilon will be E, and this is called as modulus of elasticity. Modulus of elasticity. Sometimes it is also called as Young's modulus. Y-U-N-G-S, Young's modulus. So this represents the slope of the curve. So once you make this, once you keep this going like this and this and this, at some point this will yield, and this will show behavior like this. So at some point of time, this proportionality gets disturbed, and that point is known as yield point of the material, which is represented by sigma y. This is the yield point. Now it is important to understand that most of the material gets designed on the basis of yield point only. Most of the material get designed on the basis of yield point, that they want to get. So remember that material doesn't get failed here. Material only gets deformed, which is permanent deformation kind of. So if you are loading this metal with your load, and at some point, even if you remove the load, the material come back to its original position. This is some kind of a scale. So if I have a scale on me, if I am fixing this scale at this point, and if I am putting the load, once I remove it, the material will come back to its original position. I am again putting the load, the material will come back to its original position till the time material is within this line. The moment the material goes off with this line, that means the loading curve is off with this line, goes beyond the yield point. If you now reload it, if you now unload it, that means you remove the load, then the material will come back on this curve. That means it stores some strain on this. Some strain is stored inside the material, and this represents a behavior which is known as plasticity or a plastic behavior. The storage of strain represents a plastic behavior, and when there is no storage, that means once the loading happens and you remove the load, material come back to its original shape and size. This region is the elastic region, and once the elastic region goes beyond, that means the load goes beyond the elastic region, the plastic region comes. So this all region is a plastic region. And once the plastic region happens, there is some kind of strain hardening occurs. The strain hardening occurs, material regain its strength due to the change in its molecular configuration, and material regain its strength, and it shows some more strength beyond which it gets failed. So though the yield condition of the material is this, that means the material gets the maximum loading point of the material should be like this. So most of the materials are designed at yield point, because the mechanical failure usually, even if the material gets deformed, the material is said to be failed, even it is not physically failed. So that's why most of the failure theories and failure conditions consider the material to be failed at the yield location. But usually it doesn't happen, and if you talk about theoretically, material also has one more strengthened point, which is known as ultimate strength, sigma u. This is the ultimate strength of the material. This is only 10 to 15% or some 20% higher than the yield point, and beyond which the material actually fails at this location. At this condition, materials totally fail, and as you can see, after the elastic condition is met, so after this there is a large amount of plastic strain is accumulating inside the material. That means the material is getting only deformed without any substantial increase in the load. The material is only getting deformed. Earlier the material was deforming also, and material was taking the load also. So in most of the practical conditions or most of the designed conditions, this line is very important to you, beyond which what happens for this course will not be relevant to you. So we'll be talking everything about the elastic conditions only. So this, within this elastic condition, this curve is valid. You know that because this is the condition of y equals to mx plus c. This is a condition of line. Line is only valid till it is line only. The moment it becomes a curve or a quadratic curve, this won't be applicable. So similarly, this will not be applicable. So let me give you a name of this. Sigma upon epsilon equals to E. So let me now give a name to this condition. This condition of sigma upon E is equals to sigma upon epsilon is equal to E, and this condition is known as Hooke's law. This condition is known as Hooke's law. So in a case of a Hooke's law, the stress is proportional to strain, and the important thing is within the elastic limit. So within the elastic limit, stress is proportional to strain. This condition is valid within elastic limit. That means this slope is called as E, and the condition is known as Hooke's law. This condition is known as Hooke's law, and this is only valid till the elastic limit. And where is the elastic limit? Elastic limit is till the line, when the line is linear, when it is like a line only. That means usually it is said that it is till the yield point. For most of the materials, it is till the yield point. That's why it's called as Hooke's law. So we'll talk more about Hooke's law and what is the generalized Hooke's law. We'll talk about more on this. So now let's talk about generalized Hooke's law. In the generalized Hooke's law, basically it's a three-dimensional Hooke's law. This, as you see, that this is a one-dimensional. As you apply a load along the particular direction, you will be getting strain in that particular direction. But usually in a three-dimensional Hooke's law, something very different happens. So what happens in three-dimensional Hooke's law? Or a generalized Hooke's law. I will say more on this. That's a generalized Hooke's law. Generalized Hooke's law, or a 3D Hooke's law also, you can say 3D. So in this case, what happens usually, let's say you have a cubical box, cubical element, and for this cubical element we have x, y and z. We have x, we have y, and we have z. And let's say that let's particularly apply a load particularly, but before we do that, let's make some assumptions here. Some assumptions are, the first assumption is that the material that I am loading on this will be an isotropic material. So Hooke's law is only valid for an isotropic material. That means, what does an isotropic material means? That the properties are same. The properties of the material, like modulus, Poisson's ratio, stiffness, or some other properties. The properties of the material, like thermal expansion, the properties of the material will be same along the x, along the y, along the z. It will be same. And most of the real materials exist in the in practical in practical scenarios like aluminum, copper, steel. All these are usually are isotropic materials. The second condition, which is the most important one, is the linear nature of the load. That means linear elastic material. Linear elastic material. That means the material should be linear, it should be elastic material. The material should behave the material should obey the Hooke's law. The Hooke's law that we have explained here. That means it should be linear and should be elastic. It should follow this line. That means it should follow this line. So these two conditions are important, and this second condition will be linear elastic material will be important because we'll be superimposing our stresses. Will be superimposition. We'll be superimposing the loads. So what we'll do, let's apply load along x only. So apply your load or stress along the x. So along the x, let's apply stress sigma x. So what will be a strain along this? So your strain will be epsilon x. Strain will be sigma x upon E by Hooke's law. Correct. But once you will be loading your material along the x, due to the Poisson's effect, you will be getting strains in the other two directions also. And this was the Poisson's effect. But the Poisson's effect said that as in this case, as I have applied only the linear load along one particular direction, I have got two strains, epsilon 1 and epsilon 2. Epsilon 1 was axial, epsilon 2 was non-axial or transverse strain. So that means that on the application of the linear load, linear along one direction, you get strain in the other direction also, and this is what the Poisson's effect is. So the Poisson's effect will be here also, and you will be getting the strain in the other directions also. So you will be having epsilon y also, epsilon z also. So what will be epsilon y? Epsilon y will be, so epsilon y will be the transverse strain. So in this case, this will be your transverse strain, epsilon y, and this will be epsilon. So this will be from the Hooke's law, you can put it here. So this will be nu, in fact minus nu sigma x upon E, minus nu sigma x upon E. So let's put it here. So this will be minus nu sigma x upon E. Sigma upon nu, this comes from the strain, and strain is the axial one. So minus nu sigma x upon E will be your strain in the y direction. In a similar way, what will be the strain in the z direction? In the other two, the direction, that means in the other axial direction, you will be getting the same strain, sigma x upon E. So due to the application of one load sigma x, you will be getting a strain along the x and the strain along the y and z also due to the Poisson's effect. If I will apply load along the y, so along the y, this will be sigma y upon E, and due to the Poisson's effect, I will be getting the Poisson's contraction, I will be getting the effect in the x and y, x and z also. So this will be minus nu sigma y upon E. This will be minus nu sigma y upon E. Correct? Minus nu sigma y upon E. If I'll apply in the z direction, what it will be? Sigma z upon E. And I'll be getting the contraction along x and z. Minus nu sigma z upon E. Minus nu sigma z upon E. So as you can see, this becomes strain equations for us. Epsilon x equals sigma. So this is a condition in which either I apply a load proportionally, like means in a superposition way. First I have applied x, then y, then z, or any load which is applied in the simultaneously in the x, y, z directions, you will be getting these equations. Epsilon x, epsilon y, or these equations will be valid. So they will be having like this. Further, we will be having a shear also. So if I'll apply tau xy, but where is the modulus? Like this modulus E is for normal stresses only, normal stress and corresponding normal strains. So in the case of, for the case of Hooke's law, let's come back here. For the case of the epsilon and sigma, this was normal. If I'll talk about shear, this will become my tau and this will become my gamma, and the slope will remain same, but it is not called as E. In fact, it is called as tau upon gamma, and it's called as G, and this G is called as shear modulus. Shear modulus. So my shear modulus will be effective for gamma xy. So my strain gamma xy will be equal to tau xy by G, and the other case yz, tau yz by G, gamma xz equals to tau xz by G. This is the way I have proposed here. This is only a way to explain you with the principle of superposition how to obtain the generalized Hooke's law. But the equations for the generalized Hooke's law is this. These are the 6 equations. 3 normal equations and 3 shear equations. They will be combined together, and the combined one is known as generalized Hooke's law, 3D generalized Hooke's law. And with this, with the help of this, you will be able to obtain different values of stresses and strain components of the stress tensor. So you will. So what happens in this actually? As stresses and strains are combined. The stress tensor and strain tensor earlier were separate. However, in this, the stress and strain tensors are kind of combined. So this is a generalized Hooke's law. Remember that one important question which comes to our mind is that what happens if I apply a shear stress? Does the Poisson's effect rule also occurs when a shear stress is applied? Now remember that whenever a shear stress applies or any stress applies on the body, the Poisson's ratio is a property of the body. The Poisson's ratio is the property of the body. Like for example, you have a mobile camera. So the hardware of the camera is the property of the camera, or property of the mobile phone, the hardware of the camera. The software that runs on it is the external part. If the hardware is not good, the camera will not be of any importance. So you can improve the software as much as you can, but you need to have a good hardware. So a hardware is an internal thing of the mobile or a cell phone. So it's a property of the cell phone, not of the software. So in a similar way, the Poisson's ratio is a property of the material. It is not for the epsilon and z. So a property will be applied for the normal stresses also and for the shear stresses also. So in this case also, tau xy, tau yz, when you apply them individually or if you apply them together, you will be getting the effect of Poisson's contractions in this also. But this is not seen here because this G is further related to in these equations as E upon 2 1 plus nu. This is the expression. This is the expression you can find in many books. I'm not going to derive this expression. This expression is mostly used as a relationship between E, G and nu. relationship between, if in the numerical problems you will be given only E, if you will be given only G, so with the help of G you will be calculating E and nu. So this relationship you just keep in mind, and remember that in E there exists a Poisson's effect. In all these equations of G there exists a Poisson's effect. So this is the generalized Hooke's law for you. And further I would like to, as I said, for the case of stress vector, Ti equals to sigma ij and j, and in case of strain also we have epsilon ij. So we would like to represent this or combine this together with a in a strain or invariant way. So if I look at these equations, I can make my 6 by 6 like this matrix: epsilon xx, epsilon yy, zz, or gamma xy, gamma yz, gamma zx, correct, is equal to, these sigma x, y, z can be extracted here, sigma x, sigma y, sigma z, or tau xy, tau, remember that these two things will remain sum, to gamma xy, tau xy, gamma xy, yz, and gamma zx. And what will come here? From this you can extract 1 upon E and minus nu upon E, minus nu upon E, and other 0, 0, 0. So there are 3 things: 1, 2, 3, 1, 2, 3. The other ones will be 1 upon E, sorry, minus nu, the x will come in this, minus nu upon E, because the x is on the first one, minus nu upon E, minus nu upon E, then we'll be having the y1, that means sigma y, so 1 upon E only, and minus nu upon E, and then 0, 0, 0. In this way also you'll be having one more. So what will be? It will be, let's do it, minus nu upon E, minus nu upon E, 1 upon E, 0, 0, 0. And in the other 3 we'll be having G, and we'll be having G, and we'll be having G, 3 G's, and we'll be having 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So you'll be having 6 cross 6 matrix. You can make this properly in your fashion. We'll be having a 6 cross 6 matrix. So in terms, if this is epsilon ij, this is called as Sij sigma KL. This is also called as your generalized Hooke's law. Generalized Hooke's law. Remember that this is S means stiffness, IJKL. Usually if you invert it, invert this means invert this, take an inverse of this, take the inverse of this 6 by 6 matrix. So you will be getting the term, you will be getting this equation in terms of stresses. So you will be getting sigma ij is equals to Cijkl epsilon KL. Cijkl epsilon KL, just by inverting it. So this is also your generalized Hooke's law, and remember that this is sigma ij, very well or familiar to you. This is epsilon KL, and this is Cijkl. This is a 6 cross 6 matrix, and this is very important, 4th order tensor. This is a 4th order tensor, and remember that just by knowing these values of G, E, and nu, you will be able to obtain the full matrix of full 4 by 4 matrix, full 6 cross 6 matrix of CIGKL. Remember that this is a fourth order entanglement, and this is also a constitutive relationship where CIJKL is a property matrix. So all the, like say E and nu and G, all is a properties and they are material dependent. So CIJKL will be different for different materials. This is very important here. And further you will be discussing or you will be understanding or learning more about this in your higher classes. So that's why I have made these equations in this compact form. So always remember this CIJKL is a property matrix in which the properties of the material will be there. And for the isotropic material, E, G and all these things will be there, and this is only for the isotropic material. For the non-isotropic material, these empty cells 0 will also be occupied by the other quantities. So these empty cells will also be occupied by the other quantities, and this matrix then becomes more and more complicated. So to your understanding, it's important to understand Hooke's law in this format in terms of these equations. So generalized Hooke's law is there. Any questions can be put in the comment section. I'll be happy to answer. I hope this video will be informative to you, and I thank you for your time.